Okay, so for the remainder of my lectures, I'm going to be talking about triangle decompositions. Let me remind you of some definitions and the statement of the theorem. So we want to find a triangle decomposition of a graph G, i.e. we write G is equal to the union of some T where T is a set of edge disjoint triangles. I think I'll often use the acronym SET for that because it's something which I'll have to write quite a bit. Okay, so we last time I mentioned a couple of necessary conditions on a graph G for this to be possible. So firstly, the number of edges of G must be divisible by 3. And secondly, the degree of every vertex must be even. Okay, so these are obvious necessary conditions. And if these are satisfied, we say that G is tridivisible. Okay, so last time I told you that Kirkman's theorem, which can be phrased as saying that tridivisible complete graphs have triangle decompositions, and Gustafsson's theorem, which extends this to say that tridivisible graphs of large minimum degree have triangle decompositions. So the theorem I want to tell you about is that tridivisible graphs which satisfy a certain pseudo-randomness condition have triangle decompositions. And the pseudo-randomness condition I called being typical. So we say G is C-typical if, so firstly, every vertex has degree about what it should be if it was a random graph. D of G is the density of G. And secondly, the codegrees are correct. Any pair of vertices have the right number of about the right number of common neighborhoods. Number of common neighbors. Okay, so the theorem I want to prove we introduce some constants. So there exists some C0 and N0, such that for all n bigger than n0, if G is a tridivisible graph on n vertices with density not too small, with now I could say larger than some constant, but actually I'm going to even allow it to be larger than some small polynomial. So I'll write larger than, I think, n to the minus 1 over 30,000. The number is not important. G is C0 dg to the 1 over 3,000 typical. Then G has a triangle decomposition. So I've stated this in a slightly different way to last time. I think it's
You started with C0, right?
yes. I think this is a clearer way to state it.
So the density in the degree is almost n squared, but it's like polynomialism.
Yes, and that was the key step for one of the applications I mentioned last time on the number of Steiner trivial systems.
C0d to the 3,000, not 1 over?
Yeah. Yes. Sorry. Yep. I confused myself. It was 1 over 3,000 last time. Yeah, or something like that. Yeah. Exactly. Yeah. Yes. The typicality should be sufficiently small compared with the degree.
So if the degree is greater than, if the density is at least 1/10 and it's 0 typical, is it easy? Or is it just as hard?
Well, you'd have to understand what zero typical graphs are. Maybe it's. I mean, I think they're very special, like graphs with where all the degrees are equal and all of the co-degrees are equal. Yeah, strongly regular graphs.
So is it easier in that case, or it's just as hard?
I don't know. It's I don't, off the top of my head, I don't see any simplification.
Presumably because once you start doing anything, then you destroy the property. I mean, this should be flexible enough to allow you some kind of nibbling.
Right, exactly. You'll see as when I start talking about the proof that I'm going to be applying the nibble, and that will cause the graph to become less typical, but still not atypical or something. Okay, so what's that?
What's that mean?
Yeah, I'll tell you about it. Yeah.
Kill soon.
By the end of this, you'll know more about this than you suspect.
Yeah, but just it's this semi-random method which I mentioned last time, which Rödel used to prove his result on almost Steiner systems. But I'll say more about it. Okay. Okay. So let me talk informally about the strategy of the proof. So the main idea is to use a randomized algebraic construction. Informally, the idea here is that you have some algebraic construction which doesn't solve the problem but has nice properties which resemble the problem that you're trying to solve. And by taking a suitable random subset of this construction, you can use it as a template for your construction. So it gets you started. You do something else, and then you use at the end the nice properties of the template to fix any errors which you incurred along the way. So let's write a little bit about that. So it's So it's a random subset of an algebraic model. And so nice properties allow local modifications. To turn an say an almost solution or almost decomposition into a decomposition. Okay, so what do I mean by an algebraic model? So for the problem of Steiner triple systems, there's actually a very easy answer to this. It's one of the ways in which it's simpler than the general problem. So the algebraic model for triangle decompositions. So imagine that the vertices of your graph, right, are labelled with some abelian group or field or whatever. So suppose GG contained in a gamma is such that an abelian group. And let's consider the triples x, y, z, which satisfy some equation, x plus y plus z is equal to 0, or the identity of the group. So why this equation has a nice property. If I fix x and y, there's a unique z that solves the equation. So for x and y, there is a unique z. Okay, so looks like the kind of property we'd be interested in for a triangle decomposition. Again, we want every edge to be in a unique triangle, but this is not going to solve the problem because, well, so first of all, I'm not working with a complete graph, so some of these x, y, z are will not actually be triangles in my graph. X, Y, Z may not be a triangle in G. And even if I was working in a complete graph, this wouldn't be a solution because it might be that the solution for Z is one of X and Y, so it wouldn't actually be a triple. Okay. But if we're not actually trying to write down a construction straight away, it's we'll be satisfied with covering a constant fraction of the edges by triangles of this kind. So that's what we're going to do for the to make the template.
So this one you can speak about vertices that don't exist in your graph, since gamma k may be bigger than.
Yeah. Okay, so now I'm going to state the strategy in a formal way. So I'll divide it into several steps where it'll be clear that if I can implement each of these steps, there is a triangle decomposition, and I have to work through the steps one by one. Okay, so let me just have just a bit of terminology which I'll use will be convenient. So so I'll always have so G. I'll always have G on n vertices, and if I have a subgraph J is subgraph of G, I'll say J is C bounded if J has maximum degree less than C times n. Okay, so just be convenient to say that rather than saying max degree at most C times n all the time. Okay, so so what is the strategy going to be? So so we want so we find a template. So a set of edge disjoint triangles T subset G. That will be in a construction like this. So write G star for the union of T. This will be a subgraph of G with the properties. So I'll give these properties names for easy reference. So the first property I'll call nibble. So I can cover most of the edges outside of this template by some set of edge disjoint triangles. So there exists a set of edge disjoint triangles which I'll call N for nibble, which is in the remainder of the graph, so G not in G star, with leave L, which is so the edge is not covered by N, that is say C1 bounded. So there'll be various constants which appear, C1, C2, etc., and you'll see what they are as we go along. I won't tell you now, I don't remember what they are, but we'll see. So we'll calculate C1, C2 as we go. Okay, that's the first property we want. Second property, covering. Okay, so the we've covered most of the edges which are in G and not in G star. Now I'm going to cover the remaining edges, in L, and I'm going to use triangles, and these are going to spill over onto the template. So at this stage, I will have covered some edges twice. I'm going to have to fix that later.
What is the U in the end?
Union. So the
Union of
so
It's a collection of triples, so that's just very
Yeah, it says
Yeah.
set. It's actually a set.
ACT, big
It's
ACT.
a union with
It's
the
a
a
edges.
set of
of
vertices or a set of...
Okay, so sorry,
Short.
I defined this earlier, but I should remind you. So set
As a set of edges, right?
edge disjoint triangles.
No, but you're thinking of it not as a set of triangles, but as a set of edges.
I'm thinking of a set of edges. So when I take its union, I get a graph.
A graph.
Yeah.
Okay, thank you.
Yes, I'm going to be a bit lax about whether I'm talking about triples or triangles. I hope it will be clear from the context. But, okay, so yes, I'm going to choose some triangles which cover L, but they're also going to use some edges in G star, and that's a problem which I'm going to have to deal with later. Okay, so given C1 bounded L, which is contained in G star, there exists a set of edgeless triangles. I'll call this, I think, MC for cover, such that so MC intersect G delete G star is equal to L. So set of triangles which covers its intersection with G delete G star is precisely the edges we want to cover. And this spill, I put quotes on these things, the spill S, which I'll define to be the intersection of this with G star. Oh, when I write MC, I should have written union of MC because I'm talking about a graph. This will have some other boundedness. Let's call it C2. Okay, so now I'm in a situation where I've covered every edge once or twice. Most once, and a few of them are twice. Yes. No, it's just the number of vertices. Yeah. Arguably, it would be natural to define it relative to the density of the graph, but since my graphs are very dense, there's no particular reason to do that. Okay.
Just to see that I find it. So you covered most of the edges you covered by T, and then there's a slight residue which is N, and then the way to look at it.
So it's each of them is some absolute constant fraction. The ratio is not particularly important. It will, you could think of it as half and half. But
because in some sense N is small because it is bounded and T is not necessarily bounded.
So
yeah,
so T
I
see.
So okay, so L is the small residue. N is not. N
No.
can be big.
T and N are both large. They constitute most of the decomposition, and then everything else is just trying to fix the small errors at the end.
Then you recurse on this part that's left.
No, there's not going to be any recursion. It's just going to be direct construction.
So just so I understand what you're proving, so this is your end goal of today, to prove what is now on the board, to implement this strategy?
So I won't. This is my goal for all of the lectures. So I'm going to. So I'm going to. Yeah. So. Was that? Yeah.
I say you haven't finished the plan. You
No.
can tell us what happens with the spill.
Yeah, exactly. Yeah. So I'm giving you the whole strategy, and then I'm going to sort of. I'll remind you as we go along where I'm up to in the strategy. These are just words which I'm using. Just. Yeah. It's not. Yeah. These are just names to attach to these things, so they're not just letters. You can. Okay. Next. Okay. So I want to find some way to rearrange the template in such a way that I don't cover these edges twice. So I'm going to do this in two steps. So the first step will be to design a hole, which is a subgraph of the template, but not necessarily using triangles, which are in the template. And then I want to rearrange the template so that it does actually use triangles. So So given C2 bounded tridivisible S subset of G star. I'll explain in a minute why this S is tridivisible. C2 is the same C2 as here. I'm repeating the conclusions of each step as the hypothesis of the next step. Just to, there are two sets of edge disjoint triangles. So MO, which is the outer one, and MI, which is the inner one. So and these are going to be two sets of edge disjoint triangles. One being such that one, when you take their unions, one is a subgraph of the other, and the difference between them is precisely this spill. So such that S and the union of the inner set partitions the subgraph formed by the outer set. And I also want some boundedness condition. Union of the outer set is C3 bounded, so some new constant. Okay, so what? Okay, I'll say it again. So this I've got some. This is these are in G star. So I'm working in the underlying graph of the template. I find some set of triangles and which contains S, and when I take away S, then what remains can be partitioned into some other set of triangles. Now this would be great if this set of disjoint triangles was part of the template, because what I would just throw it away, and instead of using the outer one, I'd use the inner one, and that would just solve my problem. The things which were covered twice would now only be covered once. But I don't have that. I just know it's a subgraph of the template. Okay. So the final step will be to go from this to a situation where this outer set of triangles is also a subset of is also a set of triangles in the template. Completion. So given L, MC, MI, MO, as above, we find SETs, sets of edge disjoint triangles, M1, M2, M3, M4, such that, okay, I'll write down some properties and then I'll explain what they are for. So L and the union of M2 partitions the union of M1. What else do I want? I want the the union of M3 to be equal to the union of M4. So these are two different triangle decompositions of the same graph. I want M1 to be contained in M3. Let's see. And M2 to be contained in M4. Okay, so so what am I doing here? So I'm for reasons which will hopefully come later, I'm rearranging everything. So I chose a lot of triangles which do a certain thing, and then I'm going to have some algorithm where I place triangles which I don't want by triangles that I do want. So so now I was using MC to cover L, but instead I'm going to use M1 to cover L. That's going to cover. Wait, not. I've done this wrong. Just a second. As I talk through the strategy, then I'll figure out what I've done wrong.
Would it be useful to draw
Yeah.
a diagram of the M's and the L's?
Yeah. Okay. Yeah. One of those things is wrong, so I'm going to figure out in a second what it is. Save picture. So here's G.
You have color chalk, by the way, so you can draw the one partition with one color.
Oh yeah. Okay. So maybe I'll stick to white for a second. So here's T, the union of T, and here will be the union of N. Here's going to be L, and so what am I going to do now? I'm going to find some. So here's going to be the union of M2. This is going to be the union of M1. And then what am I going to do? I'm going to say.
Where is still in this?
I'm forgetting about it. It was just a device which was going to be used to. It's going to disappear during this algorithm.
No, but before it disappeared, can you see it on the diagram?
Then I should draw a different diagram, maybe. Maybe let me concentrate on this diagram for a second. So, M2 is going to be. Yeah, okay. I see what I'm doing. So M2 is going to be contained in M4. Now this is some this is some subgraph of the template which has a triangle decomposition, but this triangle decomposition, these triangles are nothing to do with the template, they just happen to belong to the graph. But this graph has the property that it also has a decomposition which comes from the template. Okay. So this okay. So maybe this will become a bit clearer. So in fact, you could take the same picture. So think of this as S.
S is N or?
So for this you could think of this as being S, and you could think of this as being the union of. Okay, so the first picture to bear in mind, which I drawn in blue, was I had T, N, L. I covered L, and then this was S, and then I had some triangle decomposition of a subgraph which I called M outer, and then also, so maybe this one is this whole thing here is M outer, and then this thing in here is M inner. So the difference between M outer and M inner was S. Okay, so that was the first thing I said. But the problem with this was I didn't guarantee that that the triangles in M0 were triangles in T. So then I just modified everything. Once I got to this thing, I modified everything, and I got some new sets of triangles, which I called M1, M2, M3, M4, which had the same properties, but they also had the M2 and M4 had the same properties as MC and MO, but there's an extra property, which is that I can replace M4 by M3, and M3 is a set of triangles in the template. So I can write explicitly so given this strategy, what is the triangle decomposition of G? So then M is so it's T. So it's N union M1 union M4 delete M2 union T delete M3 is a triangle decomposition of G. So if I can find this setup, then I'm done. So I take N, I take M1, that's covered. I've covered this, I've covered this, I've covered this. I take now this in here is equal to M2, so I take M4 delete M2, I cover this, and the union of M4 is equal to the union of M3. I take T delete M3, I covered this, so everything is covered once. Maybe I should pause for a bit and just to let you. Say that again.
One is L union M2. Is that
That's right. Yes. So the union of M1 is partitioned into L and the union of M2.
So can you go over the principle again? The first steps in, at least conceptually, not so difficult. You pack a lot of this long triangle. The rest you overcover with just an overlap of 2. And now you want to start fixing these things. You want to eliminate these extra edges.
Yeah.
So you create a hole which, to begin with, is not necessarily a union of triangles.
It is a union of triangles, but they're not triangles of T. Yeah. Yeah.
And then how do you trade these things? How do you, so you rearrange them to become, or you give away, you give up some of the triangles in the original template for those? How do you do this fix?
Well, that's what's going on with this step here. So I mean, I've stated it all at once, but when I come to implement it, it will be a step-by-step thing where I focus on a particular triangle that I want, and then I embed it in some bigger graph, which is going to be part of both M3 and M4, and it will have 2 different triangle decompositions, one of which will come from the template, so that will belong to M3, and then the other one will belong to M4, and that will contain a particular triangle which we want to get.
So this in principle is going to be now triangle by triangle. There is a triangle that you created which is not part of the template, and you want to trade it for.
Yeah, I want to find a way of rearranging the template in such a way that so rearranging the triangles which I'm using in the template in such a way that I am using that triangle that I want. Right, but so for some technical reasons, which I'll get into not now, but later in the week, I'm just going to have to undo everything that I did because I wasn't careful enough earlier. But it doesn't matter because I can just change what I did and it's okay. So but you'll see. All right. So okay. So now. Okay, so let's start. So I'm going to. So the first thing is to tell you what the template is, and I kind of told you already, but now I'll so properly. Our template. Okay, so here's the construction. So I'm going to embed my vertex set in a finite field, and it'll be convenient for me that it has characteristic 2. So so fix A such that n is between 2 to the a minus 2 and 2 to the a minus 1. And I'm going to randomly embed, so let's pi be a random injection. So vertex set of G goes to this finite field, F2 to the A, be a uniformly random injection. I'll let so T be the set of all triangles x, y, z. So triangles of G such that they satisfy this equation I mentioned, pi x plus pi y plus pi z is equal to 0. I'll let so G star will be the union of T, which is what it has to be. Okay. So that's what I said before, essentially. Okay. So so what properties do I need? So there's going to be various nice properties I want of this template. Some of them are to do with the to do with the algebra. I'll defer talking about those for now, and I'll just talk about the pseudo-randomness condition, which is the same condition that holds for G also holds for G star with some different constant. And actually, I'm going to switch now to using a stronger typicality condition, which is the one which another one which I mentioned last time. If I can do it with a stronger condition, it's not hard to modify the proof to do it with the one I stated before. Right? I may say something about that if I have time. So from now on, we'll use a stronger pseudo-randomness condition. I stated last time I'll delete the picture. Is that okay? So now we're what's that? Oh, okay. Good plan. So I'll say G is CH typical if for all S subset of EG of size at most H, we know we have control on the number of common neighbors. So this is the common neighborhood, and it's about what it should be in the random graph. So if it was random, it would be density to the size of the set times n, and I'm going to have some approximation, and I'm going to throw in the factor of s just to make the calculations work out more nicely, but ignore that. So it's 1 plus or minus size of s times c. and I'm going to so I'll suppose we'll suppose G is C16 typical. So the condition I mentioned before was essentially C2 typical, if you ignore this. Now I'm going to say C16 typical. And believe me, for now, that this doesn't make much difference.
T captures like 1/n of
That's right, yes, yeah. And this is one reason why it's hard to find particular configurations that you're looking for using these triangles. So there are other papers, say on perfect matchings and hypergraphs, which use the kind of strategy of putting aside a reservoir, doing something, and then fixing it at the end. And these, it tends to be easy to find things you're looking for in the reservoir because it's dense. But as you point out, the density of T in the set of triangles is only 1/n. So to find some particular configuration that you want using these triangles would be hopeless if you just chose them uniformly at random. Okay, so all right, so we'll suppose G is C16 typical. Now I want to say something about G star. And actually I want some joint typicality between G and G star. I want to say if I look at I take some subsets, well, I'll write it. So we say G star is CH typical if for all S star contained in S contained in E of G, size of S at most H, say something about common neighborhoods where some things are connected in G and some things are connected in G star. So we want to look at so we're going to look at all of the G star neighborhoods of vertices in S star and all of the G neighborhoods of vertices in S. And this is supposed to behave like as if everything was random. So it's so 1 plus or minus size of S times C times density of G star, size of S star, density of G to the size of S times N.
S minus S.
Thank you. Okay, so the first lemma, so with high probability, so I know, before I say this, let me, I want some notation and a few observations. So I should have made some comment about the density of G within this field that I've embedded in. So as Natty mentioned earlier, when I write down these equations, sometimes I'm referring to vertices which are not, I'm referring to elements of the field which are not actually vertices. So I'm going to have to take that into account somehow. So let's write gamma for the density of vertices in the field. So density of G in the vertices of G in F2 to be A.
Between a quarter and a half?
Between a quarter and a half. Okay. And there's some other observations I wanted to make about the field as well. So before I get started on this lemma, so the reason I'm working in characteristic 2 is so since we work in characteristic 2, we have +1 is equal to -1. So I'm not going to worry about signs when I write equations. So and what else am I going to have? If I have a triple, so if x plus y plus z is equal to 0, then x, y, and z have to be distinct, and x, y, z are non-zero. You know what? I made a serious error. Not that serious, but and I've already erased it. So when I took the embedding, I wanted to take the embedding into f2 to the a excluding 0. So
Image of pi.
yeah, so correction. So correction. Yeah. Right. I don't want to allow 0. Okay. So if x plus y plus z is equal to 0 and x, y, z are non-zero, then x, y, z are distinct. And then another point to note, just another trivial observation, just is that if I take distinct x and y, that x plus y is not 0. So. Yeah, just working in characteristic 2 just simplifies a lot of things. Okay, so all right, now I'll state the lemma. So with high probability, I have a good control on the density of G star. So it's all right. So it's about gamma times the density of G cubed. And G star is 6C, 16 typical. Yes. Okay, so let's prove this. Okay, so let's first work out the expected number of edges in G star. So expected numbers of edges in G star. So it's the sum over all edges in G with the probability that E is in G star. So let's fix an edge and figure out the probability that it's in G star. So fix E, which is x, y, and let's condition on pi x and pi y. Okay. So now for each triangle xyz on xy, it's possible that I might choose pi z to be equal to pi x plus pi y, and then that would be a triangle in T, and then E would be in G star. So for each z such that x, y, z is a triangle of G, we have the probability that pi of z is equal to pi of x plus pi of y is equal to, so I'm just choosing a random embedding, so it's, what is it, essentially 1 over 2 to a, yeah, so 1 over 2 to the a minus 3 to be precise. Okay, so, and there are, so I just have to sum over the choices of z. There are 1 plus or minus 2c dg squared n choices of z. So put everything together. So you see where this density is coming from. There are, I've got, let me say, and how many choices, and dg n choose 2 choices of E. So so we can say the expected density in G star is, what have I got? I've got a, let's write, I've got a 3 there, so let's leave ourselves a bit of room. Maybe it's 1 plus or minus 2.1 c gamma dg cubed for small c. I won't be too careful about the constants, but you remember I had this c0, which enables me to assume that c is small. Okay, so just need some concentration inequality to say that the density of G star is close to its expectation with high probability. So this will follow from Azuma's inequality as it applies to the symmetric group. So for symmetric group. So I suppose f from Sn to R is B Lipschitz, which means if I have any permutation, I change it by transposition. It only changes the value of the function by at most b. So then probability that f deviates from its expectation by more than a decays exponentially, minus e to the minus a squared over 2n b squared, I think. So 2e to the minus a squared over 2n b squared. Okay. So how are we going to apply this here? We can think of this embedding, this random embedding, as saying first take any embedding and then compose it with a random permutation. So think of pi as sigma composed with pi 0, so this is a fixed embedding vertex set of G in the field not 0, and this is a random permutation. Okay, so what is the effect on the density of a transposition? Well, it's only affecting 2 vertices and the triangles which are sitting on those. So it's only affecting a constant number of vertices. So it only has an order 1 over n effect on the density. So any transposition of sigma only affects edges of G star incident to order 1 vertices. So dg star is order 1 over n Lipschitz. Okay, so you could put that in there and see that I can have, if I allow myself, I could have better concentration. But anyway, I'm giving away that. So with high probability. dg star is 1 plus minus 3c gamma dg. I should mention when I'm writing with high probability, actually all of these probabilities decay exponentially, so there's no problem about union bounds. Okay, right. What about the typicality? So this will be a similar kind of calculation. So next, so we consider.
Perhaps just for those who are not so used to this, these are very standard. That's how you apply martingales and Azuma. So
Oh yeah, exactly. I should make that clear. But this
so used to
yeah.
this kind of calculation, they may be.
Yeah. So yeah.
intimidating, but really
I thought I should go through it because maybe some students are not so familiar with it, but for people who are experiencing probabilistic methods, this is a very standard calculation. So next we'll consider S star contained in S contained in VG with size of S at most 16. And so I want to calculate this intersection. So that I wrote up earlier. So let's introduce some notation for it. So let y be this intersection. So the intersection over x in S star of G star of x, and also intersect with the intersection of x in S delete S star G of x. Okay. So I want to estimate, show you that, calculate the size of y with high probability. So do a similar kind of calculation. So write expected value of size of y, sum over x in VG, probability that x is in y. Okay, so what? Maybe I'll call this y because I want just. So I've been using x in S. Okay, so what's the picture here? So this is I could follow the excellent suggestion of using different colors. So G star and G. So this is what we're looking for. Okay, so what is this is Y. So so when does this occur? So I've got so I'm going to condition on so fix y and condition on pi y and pi x for x in S. And then so the property I'm looking for is I'm looking for so for each so fix y which is in the intersection, which is in the common neighborhood of S. There's no point in considering that any other y. It's not going to contribute to this. And now what I'm interested in is that for the vertices in S star, that there should be template triangles sitting on those edges, just as in the calculation for the density. So we have y in y if and only if there exists a set of zx x in S star such that we have all of these equations hold. Okay. And so we can calculate the probability of this. So one slight caveat is some of these zx's might lie in S, in which case we've already fixed them. But this is only order 1 possibility, so we can neglect those. So we'll ignore order 1 choices of y such that some zx's and some just a technical point. So otherwise, the probability that so for fixed, so given choices, so given a set of zx, sorry, I forgot to say that x and x, y, z of x is a triangle. For all x in S star. That's enough. It's not just without that, then it would be a trivial statement. But the point is that this is under these conditions. I include the triangle x, y, z, x in my template, and then in particular that means that the edge x, y is in G star. Okay, so given these choices of zx, so given such zx and this, so this event has probability, so essentially 2 to the minus a to the size of S star. So let's write 1 plus order 1 over n, 2 to the minus a to the S star. Because I'm choosing random embeddings of these fixed choices of zx. Each of them has got a particular place where I want to put it. So that's so essentially 2 to the minus a probability for each. Okay, so right, how many choices are there for the zx? So a number of choices of set of zx is, so for each of them, by typicality, it's number of common neighbors of that x and y, which is 1 plus or minus 2c dg squared n, the size of S star. So do I have everything I need now? So what else do I need? Finally, number of choices of y. So by typicality, again, is 1 plus or minus size of s, c, dg, size of s times n. So now if I multiply everything together, I should get the expression which I need in order for gg star to be typical. So therefore, let's see what we get. Expected value of y is equal to, so 1 plus or minus size of sc dg size of s times n times, so that was choosing y. Then I've got choices of zx. And then I've got the probability, which is there. Okay, so now I have to stare at this expression for a bit and see what goes with what. So here we've got a 2 to the minus a, which is going to go with that n to give us a gamma to the s. We've got a dg, we can pull out a dg cubed to the s star, and then we're left with a dg to the s minus s star. And then there are some constant factors, which, I think if you work them out, will give you a 6 there for small c. Okay, so we see the expectation is right, and a similar calculation using a Zoomer's inequality is going to show this holds with high probability. Now you see that any transposition only affects a constant number of vertices in y, and so it's so y. Oh, yeah, I got mine. So y is scaling like n, and the function, the size of y is an order 1 Lipschitz function. So with high probability, it's very close to being near its expectation. So the gamma factor is appearing in the density of G star. So right. So this when you shall I write one more step here? So this is just so it's clear what we're talking about. So this is, let's say, 1 plus or minus. So I'm aiming for 6. So let's maybe write 5.9 just to be safe. dg star to the s star dg to the s minus s star n. Okay, so this dg star has got a gamma d cubed in, so we've got the gamma to the s star from this n and minus 2 to the a, and then I've got a dg squared here and a dg here, which I pull out, and then I'm left with dg to the f delete s star. Okay. So as I said, I need some other later in the week I'll need some other properties of the template, but for now this is what I need. Okay, so this sets me up to apply the nibble to G delete G star, which was the next step. I think maybe it was the first step. So what do I want to say that this implies that G delete G star is so this implies that G delete G star is, let's say, I think 50C typical. So we just have to calculate. So let's start with the vertex degree because that's easy. So the degree of a vertex in G delete star is just the difference of the degree in G, difference in G and G star. this is 1 plus or minus C density in G minus 1 plus or minus 6C density in G star times N. So, okay, let's rearrange this. Maybe we'll write it as dg minus dg star N plus or minus 6C dg plus dg star N. So I've pulled out the main terms as dg delete g star, because that's dg delete g star, and then the error terms, I've got a 6c dg star n and a c dgn, but why not call that 6c dgn? And I was careful to choose G star to be not too dense and not too sparse. You remember it's dense. Well, actually, I've got this D as well. But you remember that gamma is between 1/4 and 1/2. So it's so I just say that this is less than 50 C D G star. Okay, and then so that's an easy calculation for the vertices, and then for pairs of vertices, I need to use inclusion-exclusion to get the intersection. So the pairs. We need inclusion, exclusion. So right, so I want to look at the common neighborhood of some pair U and V in G delete G star. So what do? I start with the common neighborhood in G. I subtract off the mixed neighborhoods where one is in G and one is in G star. And then add back on the things which were double counted, so things in G star, common neighborhood of G star. And then each of these I estimate using the typicality, so it's conscious that I'm short on time, so I'll give one more step and then so 1 plus or minus 2c dg star dg squared times n, 1 plus or minus 6c dg times dg star, and same thing again. And then add back on the same thing but with dg star squared. Okay, so each of the terms I estimate individually, and then you can see that the main term is going to pull out to be precisely what it should be, density of G minus G star squared, and then the error terms are suitably small. So I'll just skip to the what it's supposed to be. So yeah, I didn't have to. I didn't have to do it for just for pairs. I could have done that more generally. That calculation which I just did. Is that what you're?
Just saying that
Yeah.
if graph G is something typical in G prime and is something else typical in G minus 1 prime is
You
something.
also need like G and G prime together to be typical.
That was the point about making them jointly typical. If you just consider a typical subgraph of another, then it's hard to say anything about these intersections. Okay, so this sets me up to apply the nibble to G delete G star. So I stated Rödel's result last time about the existence of almost designs. So this was subsequently developed to and generalized. So nibble. So this is a semi-random construction method, right? You want to it's semi-random method, which is used. So first has many uses, but the use which I'm interested in here, the original use, is finding perfect matchings in hypergraphs. So I'll say, for example, for finding almost perfect matchings in hypergraphs. Okay, so what? Maybe just a few words of definitions about what I mean by this. So, so just as in graphs, a matching in a hypergraph is a set of disjoint edges. So. Perfect matching is a matching that covers all of the vertices. So almost perfect is covering almost all the vertices. And the particular hypergraph that we're interested in here is the triangle hypergraph of some graph. In this case, G delete G star. So given the triangle. So the triangle hypergraph, or I could say 3 graph, because its edges have size 3, H of G delete G star. So the vertices of H is G delete G star, i.e. the edges. And the edge set of H are the edge sets of triangles, so it's the set of all. Okay, so a perfect matching in H is the same thing as a triangle decomposition of G delete G star. Okay, and so the result of Pippinger extending Rödel's result is that you can find almost perfect matchings in hypergraphs under quite general conditions. So you just need them to be approximately regular and have small codegrees. Pippinger. So informally stated. So approximately regular R graphs with small codegrees have almost perfect matchings. So approximately vertex, so when I say regular, I'm thinking about the degrees of the vertices. Look at the number of edges containing a vertex, that's approximately the same for all vertices. Co-degrees, I'm talking about pairs. For any pair of vertices, the number of edges contained by that pair is much smaller than the degree of the vertices. I'm not going to state this precisely because actually I'm interested in a particular hypergraph, which is this one. And so if we think about the degrees in this hypergraph, so the degrees are just for fix an edge, how many triangles are on that edge. We know that by typicality. And the co-degrees, you fix two edges, there can be at most one triangle, 0 or 1, so much smaller. Yeah. Okay.
Density requirement for this?
Well, so if I'm saying approximately regular, then implicit in that is going to be, well, actually, when yeah. So when I say the co-degrees are small, that's going to imply that the hypergraph is large, because small would be 0 if you want, assume it's large, but that's a redundant assumption when I say the co-degrees are small, because or it could be empty, in which case it wouldn't be true. It could be empty. Okay, assume it's large. Okay, and so I'm going to apply this. Yeah, so nearly done. Just write the conclusion I want for this. So this is what did I say? I had this. This was the first step which I wanted in my strategy. But there was almost. There's just one thing to be careful of. Almost perfect means that the number of edges which are not covered is small. But I wanted a stronger property. I wanted the leaf to be bounded, so that has small maximum degree. So that doesn't, it's not a consequence of the statement, but it follows from the same proof. So the same proof allows. Gives L, which is G, believe, C1 bounded where with say C1 is let's say C to the quarter. Okay, so that was the first step which I wanted to of my strategy. I wanted to accomplish. I took the template and then I covered almost all of the edges not in the template by this n, and the leave is bounded. It has small maximum degree.
Will you prove it or just quote it?
I'll quote it. Yeah, I would.
So there is this Pippinger theorem, which is a refinement of original Frankel Redel, but then we knew how this Redel theorem gives you approximate the design.
Yes.
So can we see already here where is the extra thing which will allow us to get the full design?
No, because I didn't tell you the extra property of the template, which is going to. I showed you this picture of how I'm planning to make the modifications, but I didn't yet state the property of the template, which is going to allow me to find these M1, M2, M3, and M4.
So there is still another ingredient coming up, which is not of the nature of the needle?
Yeah, so I mean it's all to do with this construction. I want to so I'm going to I'll give you a preview of this. I want to count subgraphs of this template, which are not just subgraphs, but I'm going to attach linear forms to the vertices, linear forms and some variables, and I'm going to be interested in embeddings of a subgraph which are realized by assigning some particular values to the variables in those linear forms. And this is how I'll get around this problem I mentioned earlier of the template triangles only having density 1 over n. So it's if you're only interested in particular configurations which have some additional structure, then there is a constant density of such configurations in the template.
Okay, so let me just make a small announcement. So lunch today is not in the same place where you went yesterday. it's in the French art. It's